Sure thing. So my name is Archit. I'm a postdoc at Argonne National Lab. I've been working on like chemical language models for about like a year now. Um, and yeah, I mean, I'll just give an overview of chemical data, and so it's going to be probably much more brief than Alex's discussion. So I'm just going to talk about smiles and selfies and like different chemical data types very briefly. Just give me one sec. Let me share my screen. Is everybody able to see this? If not, just please let me know.
Yes. Yeah.
So this is also on the same GitHub that you accessed Alex's tutorial. And so yeah, please follow along with this. So I'll be talking about, as I said, I'll be talking about chemical data in general. And so just to give a very brief introduction for anybody who may not be familiar with how compounds are arranged, uh, they're just combinations of different atoms in the periodic table. And the molecules that I'll be discussing here in terms of like the chemical language models are small molecules specifically. So, and in particular, I'll be focusing on small organic molecules. So these are organic compounds that contain carbons. And so the compounds that I'll be focusing on here mostly have like carbon, nitrogen, oxygen, phosphorus, sulfur, and hydrogen because I'll be focusing on molecules for life. However, in general, you have I mean, almost infinite number of possible different combinations of molecules that we can actually talk about here. So those would be the inorganic small molecules. And additionally, so as Alex alluded to, there's also polymers. So polymers would be different monomers, so different small molecules stitched together to create much larger molecules. And so Alex, in his talk, talked mostly about nucleic acids and proteins as different polymers that you can also consider as a compound. But besides that, there are also lipids, and there's also carbohydrates that you can also consider as a polymer. And so now that we have this information, the idea is how do you represent this? How do you actually insert this into some kind of model that you might want to actually use to either generate new compounds or to learn different properties? And so one of the ways that you could represent these compounds is as graph structures. And so that's pretty straightforward because if you look at any of these compounds, they're a series of atoms. So for example, a carbon atom here, a carbon atom here, a carbon atom here, and then all connected with these molecular bonds. And so it's very straightforward to just think of this as a graph structure. As you can see here, this molecule can be sent into a bunch of nodes and edges. This can then be sent into a weighted adjacency matrix in order um, to represent this as a graph structure. And so this is useful because using this kind of graph structure, it's pretty simple to understand. It's also easy to visualize, and many databases contain like graph structures, and also analytical data such as like NMR can be easily integrated into graphs like this. So a disadvantage of using just these 2D graphs is that you can lack spatial information, and you also can't account for flexibility in the compounds themselves. And so before I continue, are there any questions up until this point?
Keep going.
Okay, so yeah, I think I'll save the coding examples maybe until the end. But I'll just have you construct your own adjacency matrix or your own graph structures from a molecular compound. So you can see it'll end up looking like this. And so another type of data, still continuing this idea of two-dimensional and like structural data, would be three-dimensional data. So this would be data that has like bonds coming out of like this bond here, and then like a bond coming out here or coming here. So actually representing that in 3 dimensions. And so that's kind of in terms of the amount of representation you're giving, that would be kind of almost considered like a gold standard because that can give you information about the molecular geometry, the stereochemistry. So stereochemistry being like, are there molecules that point this way or point that way? And are there molecules that are mirror images of each other? You can also get the conformational analysis from three-dimensional data, and it's also easy to visualize. However, the limitation is that there's a lot of computational resource requirements then needed for this 3D data, and a lot of the data might also not be extremely accurate because it's based on the crystallography data. But so the idea of this conference is foundation models. So we really want to understand, um, in principle, language, sequential data. And so Alex was talking a lot about the representations for genomes, the representations for and also for amino acids can also have their own representations. But then it's not as straightforward for compounds because if you think about it, proteins, it's you can just represent them as like these different amino acids. So those would be like the valine or alanine connected to maybe like a lysine. So it can be represented almost like a sequence like this. But if you look at a structure like this, it's not very intuitive how you would convert something like this into a sequence. And so what you would need to do is you would actually need to design your own kind of chemical language. And so that would be something that has its own grammar and has its own kind of like its own syntax, basically. Because I mean, you could start here, you could start here, and then there's branches coming off of here, there's branches here. So it's like, it's honestly very, a bit convoluted and difficult to actually think about how do you convert something like this into a language a priori. Um, but that's something that was discussed heavily in I believe in the 80s when they designed the SMILE system, which is very simple, but it's very powerful. And so this SMILE system is effectively able to take any compound with any type of branching or any type of uh, like atom types and then insert that into this chemical language. And so I'll discuss and just give you an overview of how these SMILEs work and why they're so powerful. So first off, these SMILEs actually are able to, so I mean, they're able to account for both the atoms as well as bonds. And so all atoms, if you have any atom within this SMILE string, an atom such as C would represent CH4, so that would represent methane, or sorry, it would represent uh, it would represent the valence basically. So if you have an atom like carbon, ideally carbon has four like hydrogens connected to it, or four kind of bonds connected to it. And so this carbon, since it's double bonded to a carbon here, you would have two hydrogens at each of these carbons right here. And so this is represented in the SMILE string, where you can represent C by itself without the H2, and then a double bond, which would be the double bond here, and then another C right there. And alternatively, you can also represent this as CH2 and then another CH2, which would also represent the way to represent this, like these two atoms bounded to each other. Additionally, you have it also can account for charged molecules. So if there's any molecules here that have charges, they're simply just the atom plus a positive or a negative charge. And then the very interesting aspect of this would be branched molecules. So if you have any branches within the sequence, then you can actually indicate that as a parenthesis. And so you essentially can have, and I think put it here, you can have a parenthesis. And so if you have a compound like this, like phenol, you can follow along it. And then once you reach the branch point, you can just indicate it with a parenthesis and then an O right there. And this system is also able to take into account cyclic structures, so structures that have like a ring structure to them, by simply indicating the start point with a 1 and then continuing along the ring structure until you reach the end. And finally, these these small strings are also able to represent structures that have aromatics. And so you could represent this as this type of structure right here, but you can also represent it using a different format where uh, any aromatic atom, so aromatic just means that you have a double bond that's connected to another double bond here. Those types of molecules can be represented with lowercase, like this. And finally, you can also represent disconnected structures. And so I think the takeaway with these small strings is that they're very, very powerful and very simple. So just like understanding this simple grammar can allow you to take in any type of molecule and then reconstruct some kind of text representation that you can use to actually represent that. And so what I'll have you do is so there's an API with PubChem where it'll allow you to take in any compound, so any name for a compound, such as glucose, which is essentially sugar. And you can input this and you can actually obtain the smile string automatically using PubChem, which is essentially a repository for multiple different compounds. So I'll have you do this after. Um, but there are a few downsides to using smile strings. And so one downside of using the small strings is that, and you might have realized this when I was talking about this. So a lot of these structures, especially things with branches like this, you can see that there's a branch right here at C. And so the way that these rings are actually working is that you're starting at a certain point, then you follow along that ring structure until you reach the end of that ring. And if there's a branch, then you can just account for that branch with the parenthesis. But essentially what can happen is that you can actually generate multiple smile strings for a single compound because you could start the process here and continue downwards, or you could start here and continue this way, or you can start here and continue this way. And each of these would generate a different, essentially a different smile string for you. And so this can be, it can be kind of an issue because it's not going to be a one-to-one mapping. And then another issue with these smile strings is that, and this issue might actually be more dangerous, especially for generative AI, because generative AI, especially generative like language models, want to take in a set of small strings and they want to learn on that syntax and then generate new small strings based on that. But the issue there is that the way that they're generating these small strings typically, especially with transformers, is it's going to be autoregressive, where you can build up like tokens by tokens. But if your tokens, for example, are like a parenthesis here, then that generative AI, it might just generate a parenthesis in the wrong place. And so you can actually end up with a situation where the generation of new compounds is just invalid um, because even though the machine learning model is learning the grammar, it might accidentally place something in a random location. And so ideally for some kind of generative model, this this language should be something where any different combination of these kind of words within this language should be it should generate something that's meaningful. And that's actually a really difficult thing to ask for. Because if you think about English, any word that you say, any sentence you say in English or any word you say in English, that's highly dependent on the order of words that you use. And so you could say a word like I took the dog to the park, but if you say I dog took park the, then that doesn't make any sense. And so what was designed in around 2020 was an attempt to actually generate a language where you could generate any combination of different elements of that language, and you could generate something that makes sense, something that's valid. And this language is called selfies. And unfortunately, for some reason, chemical language likes to use these very funny names like selfies and smiles. But the way that these selfies are working, and it's honestly pretty complicated, is that they're following a similar idea as smile strings, where you start at a certain location and then you continue along the sequence, and then you go to branches. But what they do is they actually have a syntax for indicating whether or not something is part of a branch or not. And the syntax is kind of interesting because um, it actually looks very similar to like atoms. And so like if you go through this sequence right here and you reach this branch point, this C right here, even though it actually looks like a carbon atom, that's just indicating that you have one branch there. And so by doing this, by including these kind of tokens as like indicating kind of numbers or indicating like these kind of like having it so that a token can represent both a number, so it can indicate that you have one branch here, or also representing an atom, makes it so that when you generate new selfies, then you can um, you can generate some things that make sense, uh, no matter what kind of order of these different tokens that you're actually outputting. And so with this, yeah, this is a very brief discussion of selfies. We can go back and we can kind of go over some of the short code snippets that I have for this. And before I continue, are there any other questions that anybody might have?
Yeah, I think we're good. Keep going.
Okay, cool, cool, yeah. Okay, then yeah, then we can go over some of the code. So we can go back to this part right here where we're talking about the 2D data, and then we can actually look in and we can actually generate, and we can see how these graph structures are actually looking at these compounds. And so this is just taking in caffeine, and then yeah, I'm first just going to draw it using RDKit. So RDKit's an engine that lets you, or it's like a software that lets you deal with these chemical data. And so I'm inputting here just the smiles for that caffeine, and then you can draw that image using RDKit. And then the interesting part here is that you can actually you can convert this RDKit object to a network X object, which is a kind of an API for dealing with graph structures. So you can generate this graph structure. You can add nodes to this graph structure, and then you can also add bonds into that graph structure. And then if you can go in here and you can actually use this function, and you can generate the graph from the molecular structure for this caffeine. And you can see it ends up looking something like this. And so what this does is this is a graph structure that you can then input into your GNN model. So is that everybody following along, or are there any questions as I go through this?
Yeah, good so far.
Okay, cool. So then the last few things we can do are talking about smile strings. So this is just using PubChem API to actually download your smile strings according to a certain like certain compound name. And so this is just using PubChem Pi, and then you can import that as you can import that PubChem Pi, and then uh, just get your compound. So glucose, you can get that and then get a name. And then you can print out the small strings from that. And then the final code that I have here, and I'm going to discuss one more thing after this, is selfies. So I talked about using selfies instead of smile strings, and so actually the API for selfies actually has a very simple interface for converting between selfies and small strings. And so in order to do that, you can yeah, you just have to install this selfies API, and then you can import that. And so it would just be selfies.encoder to encode in a smile string, and then a decoder function to decode out the smile string. And you could see that it prints it out as this smile structure like this, where you have the C, C, or double bond C, C, double bond C, C, double bond C, and then you have an indicator for a ring structure, and then there's going to be a branch one structure, which the branch one, I think, if I remember correctly, indicates that there's 6 in that particular selfies. And so you can also output the encoded small string. So yeah, this kind of concludes this notebook. So I have one more thing I want to talk about. But does anybody have any questions about this like very brief introduction?
No, I think we're good. This is great, Archit. Yeah.
Okay, cool. So one last thing I wanted to talk about, and this is something that I honestly probably should have included in this notebook, but this is an idea that I'm having, which is kind of it's related to work that's been done at Argonne before. And this would be in the idea of scaffold graphs. And so we talked about these molecular structures. We talked about these small strings. We talked about the graph structures. But one other way of representing these structures is not only how they're represented in terms of their own grammar and their own structure, but also how are they represented in terms of other compounds. And so this was actually work that was done at Argonne, especially with someone known as Austin Klein. So that was about like 2 or 3 years ago. And so the idea here is that you can actually create a graph structure. So you can actually create a graph structure with different compounds. So here I think it's showing amoxicillin. And you could say that there's certain elements of this graph structure that are shared between different compounds. So for example, amoxicillin and penicillin would have a lot of similarities with their structures. However, penicillin would have an additional NH2 here and then an additional OH right there, making it amoxicillin instead of penicillin. And then piperacil would share a lot of structures from here, but you could build out another structure right here. And so this idea is this idea of building a scaffold graph along all of your different compounds. And so the kind of the work that I've been, I mean, like, or at least thinking about, or is constructing a molecular foundation model using this scaffold graph idea. So this idea that different compounds might inherit different elements here. And can we synthesize a graph structure from all of these different compounds uh, that can be inserted into a model and actually do like property prediction using this kind of scaffold graph algebra? And so this is the kind of the last thing I want to kind of end on in terms of talking about data is this idea of using not only the language, but also using this kind of scaffold graph idea. Does anybody have any questions about this?
Yeah, 1 second.
Yeah, yeah, go ahead. Yeah,
Yeah, it's one question.
yeah, go ahead.
So I think there's some prior work on doing like the Merkle scaffold based generation or property prediction. So is this something
Uh-huh.
similar to that, or is this
Yeah,
different?
so this would be something similar to that I'm kind of working towards not only property prediction, but also this idea of generation. So like the kind of things that I was thinking about was if you can just create this, so there's like the scaffold graph API that will create the scaffold graph for you, but if you could embed each of these with maybe like the output embedding from like a generative model, then maybe that could you could generate new nodes and new like edges of these different scaffolds, and then you could use those nodes to uh, basically output new compounds. And so it would be kind of in the similar vibe of property prediction, but I was thinking more of kind of also like generation. Does it
Interesting.
answer your question? Yeah,
Yeah, thank you.
of course, yeah. Any more questions about this? Or about the smiles or selfies?
This is a really cool idea. It feels like you're kind of getting at almost like functional groups and trying to like identify
Yeah,
them and build it up. Um,
exactly. Yeah.
and I think like because like you kind of hit on it. Like one of the big, like more kind of like annoyances with files is that you have these ring structures, that you have these
Mhm.
branches that create kind of like disjoint segments almost
Mhm.
within the actual string. I wonder if they're, yeah, it's, yeah, could be cool to figure out a way to like actually, because basically like today, right, all tokens are currently continuous, but this is essentially
Yeah.
non-contiguous tokens.
Mhm. Yeah, essentially, yeah. Like it's really cool. Yeah, yeah. It's still a work in progress, but it's just an idea. Yeah, so, yeah. I think. Yeah, I think the difficulty would be definitely like how would you actually encode that into that kind of language? But yeah, it's really interesting.
Yep.
Yeah.
Cool. Something to pull on during the hackathon
Yeah,
and later.
of course. Yeah.
Cool. Anything else for now, or should we take a short break and then?
No, I think that's it from me. Yeah.
Okay. Then we'll take a short break and then do tokenization.